Hello everyone, I'm happy to have you here, and I will tell you about an intellectual system for fast and reliable automated code description development. So we will talk about our team, then we'll state the problem and the methods we solved it. Then we'll talk about the data labeling and training the model with such data. And then I'll show you the system, the in-field testing results, and we'll switch to the conclusions. So the team. We have quite a big team with different researchers, IT architects, and so on. And we are all aimed to solve one problem, which is quite a long time, which takes a manual description of core, and we want to free the geologists a lot of time to uh, get rid them of such a routine task like core description. So it is obvious that the faster we will get the description of core, the faster we could process the data and get the finite geological model and use it in production. So as this idea is obvious, a lot of works exists who try to solve such a task, but still there is no, for some reason, there is no, well, system which will give the geologist the desired description. And we wanted to close this gap, and we close it with modern techniques, which is deep learning. As you can see here, we use several architectures. First is for classification and another one for semantic segmentation of images pixel by pixel. I will tell you about it a bit later, why we used these two specific architectures. And for incorporating the system into a production-ready product, we used these white tools, which are open source, to construct a web application. So we collected quite a lot of data from different data sources, and as you can see, it is quite the variance of these data is quite huge. So this is one of the problems that can appear when you training an algorithm, but with the application of different augmentation techniques, we able to solve such a problem. So the main class which we used is lithotype, which is a rock, a type of rock with some structure. So to prepare the data, there are two steps. First is segmentation. One, we created such image mask for segmentation task, and then we used such masks and the algorithm we implemented to extract the core from the boxes, and then to slice it in such small pieces, 10 by 10 centimeters. So after we sliced the data, we took the data tables with the description and use this information to process the images to different classes. But unfortunately, the depth referencing wasn't always good. So we have to give this information and develop such a label tool to check all the data manually by an expert. So our colleagues from MIMGO gave us a task to develop a model for sedimentological description. As you can see here, we've got 14 different classes from heterogeneous rocks. It is sandstone, shales, heterogeneous rocks, and so on, with some structures. And after all this post-processing, we eventually got around 40 to 350 images per class. And as you can see, during training, we received such matrices for the validation set. So all this was incorporated to a system, which I will show you right now. So as you can see, we have a web interface where we can upload images. The images have depth referencing in their names, so the system can process this information to automate the depth referencing. So uploading the images to the server. And the first step we should to do is to set the core lengths, so these column lengths. And we also can check the depth referencing results and maybe even edit the image if we need so. The second step is core selection. As I mentioned before, we trained a semantic segmentation algorithm. So this algorithm classifies the image pixel by pixel, so we can actually understand what part of an image is as a core and which one is not. So previously we selected the core direction, and with this information we can automatically depth reference the images. So and each column, of course. So we can tweak this data if we need. And on the third step, we can further do some final tweaks for depth references. And also we can download the data which we received after splitting the image to separate columns and combining it to one large column. So now the backend prepared the images and we can download them. And the next step is classification. So this step is aimed to help the geologist get the description of core as fast as we can, and it usually takes only like several seconds for 1 meter of core. And as you can see, there is a lot of different leukotypes here. Now we pressed the apply button and the data was sent to the server to predict the classes. So we have this stitched core. We downloaded on the previous step, and as you can see, they are all depth referenced in such tables. And it can be easily imported to some other programs. So we received the classification, and the user can check the classification errors here. And if he disagrees with some of this class, he can easily change them. Also, he can select and edit the borders if they are not correct. And also he can choose and add some of leukotypes. So we can also download this data and import it to some programs. And as you can see here, we received the legend table report, and also we could download the graphical report which was presented. And if user will add some of his own classes, they will also appear here and here. So all this can be transformed to any shape and form and label which user wants to. So back to the presentation. We made an infill testing of the system and classified 50 meters of core. And after the classification results were processed by an expert, we received this classification error. So basically, 50 meters of core can be processed with the classification checkup for 40 minutes, which is a big speed up for an expert, and he can easily add some his own classes to the final description and get rid of this routine of core description. So I hope this was interesting. You're welcome to ask any questions. You can also test the system by yourself. And we are always open for any types of discussion. And thank you for your attention.